Hi there. So far, we have connected linear kinematics to angular kinematics by recognizing the relationship between linear kinematic variables v, x, a, and so on to angular kinematic variables in theta, omega, and alpha. Since kinematics, linear and angular, are connected and can be derived from one another, the next logical question to ask is, what about dynamics? That is Newton's second law. Are they somehow connected from linear motion to angular motion? The answer is yes, because that's only logical, and physics is logical, even though sometimes it may seem it is not. Anyways, we know Newton's second law is the summation of all the forces acting on an object equal to the mass times the acceleration. Right? So acceleration, as we have learned, is a cause of an external unbalanced force acting on a system or an object. So the next job would be to identify the analog of F, M, and A for angular motion. Now we have already established the analog of A in angular kinematics is alpha, the angular acceleration. But what about mass? Mass of a system defined Newton's second law, and mass was defined to be the inertia of the object. What is the similar quantity for angular motion? Now, to look closely at mass, we know that inertia, or the mass, is the property of an object that makes it harder to accelerate. In other words, by mass, we mean how hard it is to make something accelerate or change its state of motion. That is what mass or inertia means. We are looking for a similar quantity, right? That means we ask the question, what is it? What property of an object it is that makes it harder to accelerate, but in an angle or a rotational motion? So what tells us how difficult it is to give an angular acceleration to something? It turns out that the property that defines the difficulty, or that determines the difficulty in making something accelerate angularly or give something angular acceleration, is the moment of inertia. Alright, it is given the name moment of inertia, which is symbolized by I. Now, what is moment of inertia, and how do we calculate moment of inertia? That's the next question to ask. Let's look at the concept of moment of inertia a little bit more deeply. Moment of inertia is said to be depending on mass of the object or the system you're looking at, how that mass is distributed, and the axis of rotation around which the object or the system is rotating or trying to rotate. To examine these properties or these dependence factors, let's look at how this pen can be manipulated to rotate. If you hold this pen at the center, right, like this, it is easier to hold it fixed. By that I mean the pen tries to rotate, but it is easier for your hands to stop the rotation. But if you move your fingers and fix it at one end of the pen, then it becomes harder to keep it steady. Why? Because the weight of the pen, which acts through the center of mass, which is around somewhere here, will try to cause the rotation of the pen like that. If you move this axis of rotation, we are seeing that the tendency of the pen to rotate increases. Therefore, the mass of the object is, how is it causing, or how is it determining moment of inertia? Well, if you have this pen and if you have this pen, a heavier pen, it is different. You feel different when fixing your fingers to hold this pen steady. That's how the mass is determining the inertia of that particular object. How the mass is distributed for these pen-like structures, the mass is distributed, or mass acts through the center of mass of this pen or that pen. But when you look at objects which are more different, with a varied number of shape, like this cup right here, it is harder to tell through which point the mass is acting, right? Hence, this is also a determining factor. The axis of rotation, as we have seen while examining the pen, if you move your axis of rotation, then it is harder to keep the pen steady if you move it away from the center of mass. So this is also a contributing factor to how hard it is to give something an angular acceleration. So if you move your fingers away from the center of mass of the pen, it becomes easier to cause an angular acceleration for the pen, right? That's why we have to define, or we have to formulate the moment of inertia for different shapes differently. For example, for objects that are point-like, that is, objects that we can often say that they don't have any definite shape, so let's consider them to be points. And if that object is rotating around a fixed axis x like this, then the moment of inertia is determined by the distance away from the fixed axis of rotation to that object and the mass of the object. I equal to mass times radius squared. It is not actually the radius, it is r is determining the distance away from the fixed axis to the object. In this case, this seems to be the radius of the rotating object. The SI unit, therefore, can be read off from the formula directly. It is kilograms meter squared, because mass is measured in kilograms and r is measured in units of length, which is meters. So r squared is meter squared. If you have a collection of these point-like objects, then we have a system. And a system of point-like objects will have moment of inertia. The same formula, but summed over I, meaning for each object we have to find the moment of inertia and sum them up to give the total moment of inertia of the system. Ri is the distance of the ith object from the fixed point, and mi is the mass of the ith object. Now, what about objects with specific shapes that we cannot model as point-like objects, like a ball or a CD or etc., right? The moment of inertia for these kinds of specific shape objects can be calculated using geometry. Thankfully, we don't have to do that because more clever people than us have already done that and wrote them down in an organized form in the table of moment of inertia. You can find many tables of many different shapes of moments of inertia. Just Google it, right? However, not all shapes are given, and also the moment of inertia for these specific objects or these specific shapes that are tabulated are calculated about an axis that passes through the center of mass of the object. All right. So what about if we change our axis of rotation like we did for the pen, when we moved our axis of rotation from the center of mass to one end of the pen? Then table of inertia is not completely helpful, but it does play a role. The solution to this predicament, that how do we get around the fact if we change the axis of rotation away from the center of mass, well, then we have parallel axis theorem, which states if you know the moment of inertia I about the axis passing through the center of mass, then the moment of inertia about an axis that is parallel to the first, that is parallel to the axis through which is passing through the center of mass, is given by the parallel axis theorem, which has the formula or the equation I being the total moment of inertia for about the chosen axis, which is away from the center of mass, equal to I about the center of mass axis, which you can find for specific shapes using the table, or for point-like objects using our formula. Take that and add it to m, the mass of the object or the system, times the distance, or capital D squared. What is capital D? This is the distance between the old axis passing through the center of mass and the new axis which is parallel to it. Now I can talk about it for more than an hour, but the best way to get more of a clear point of view about this is jump into examples. So let's do that. So let's jump right in. We have 3 kids going around in a merry-go-round, and they're standing as shown, 1, 2 and 3. The fixed axis of rotation is right at this x here. If you can make this x out, it's basically at the center of the merry-go-round, and the merry-go-round is rotating counterclockwise like this, and the children are stationary on this merry-go-round going around. What is the moment of inertia of the kids? So let's look at what the system is. The system consists of 3 children, 2, 1 and 3. So the moment of inertia is a combination of particles or objects. Now, what shape are these children? They can be of different shapes, right? So they are basically what we call rigid bodies, and they don't have specific shapes. So what we do when we model things like human beings, we consider them simply as particles or point-like objects. Okay? So if we are asked to calculate moments of inertia for kids or human beings, model them as point-like objects. It's not accurate, but physicists are not that smart after all. Let's go about solving our problem. Now, moment of inertia for a system of particles was defined as I equal to the summation of over I of the product of mass I times Ri squared. R is the distance of each of these ith particles or objects from the fixed axis of rotation. In this case, we have 3 masses and 3 distances. So m1 r1 squared plus m2 r2 squared plus m3 r3 squared will be the total moment of inertia for the system. If we have the masses down, then we can just plug them in. m1 is 30 times the distance of 1 from the fixed axis is 0.5. So 0.5 squared plus m2 is 25 times the distance is 1. So 25 times 1 squared plus third kid has a mass of 33. So 33 times the distance is 1.5 squared. Therefore, moment of inertia is 107 kilograms meters squared. This is the moment of inertia of the kids going around in the merry-go-round. Let's look at a second example. Let's say we have a pen that we hold in our hands and try to make it rotate by holding it fixed at different positions. So let's try and rotate it when I hold it like this, or maybe I hold it like this. It becomes easier to rotate. So this is another proof that moment of inertia is also dependent on where you hold this pen fixed. That is where you fix your axis, okay, about which it can rotate. So let's say you hold it along the length of the pen in different directions and try to rotate. What is the moment of inertia of the pen if you hold it at mid length? That is the center of mass. So right about the middle of the pen here. So let's see what it looks like. Pen is a shape that cannot be modeled as a point-like object because these are not points, right? It has a specific kind of shape. Now, the closest shape that we can approximate this pen to is what we call a thin rod. Okay? If we model it as a thin rod and we fix our axis of rotation at the center of mass, okay, this is our axis of rotation. What is the moment of inertia for this pen? Thin rod has a moment of inertia given to us as 1/2 ml squared. This is directly collected from the table. The table gives me the moment of inertia of a thin rod when the axis of rotation is at the center of mass. Okay, so the direct answer to the first part of this question, what is the moment of inertia if you hold it at the center of mass, that is if you fix your axis of rotation at the center of mass, we can just look at the table and write the answer down because we have modeled the pen as a thin rod, and the moment of inertia about the center of mass axis is 1/2 ml squared. M is the mass of the pen, L is the total length of this pen. So it is this length, L. All right. Now, the second part of the question asks, what if you hold it in a position that looks like this? So we have the rod here, right? Okay. What happens if we fix our axis right about here? This is our axis of rotation. Okay. So we have moved to one end of the pen. Now, what is the moment of inertia? Now we cannot directly write it down from the table. We have to use what we learned to be the parallel axis theorem. Okay. Now let's put that knowledge into use and see how this actually works. We have this axis which is at the end of the pen. Our job is to find an axis through the center of mass which is parallel to this axis. What would that be? You simply draw a vertical line through the center of mass of the pen, and you can see that this axis, that is your now fixed axis, is parallel to the center of mass axis. Okay. Since these two axes are parallel to each other, we can use parallel axis theorem. How do we use that? The length of the pen is still L. The distance from the center to one end of this rod should be L over 2, half the length, and it so happens that L over 2 is the length or the distance between the two axes you have chosen, the center of mass axis and the axis which you are holding fixed while trying to rotate it, right? So using parallel axis theorem, which told us I equals I center of mass plus mass of the object times the distance between the axes squared, the I center of mass is nothing but 1/2 ml squared from the table, 1/2 ml squared. Mass of the pen is, let's keep it to be m. What is d? D is L over 2. It is the distance between the two axes. D squared would then mean L over 2 squared. So what do you have here? We have 1/2 ml squared plus 1 over 4 ml squared. If you add the two, you end up with 1/3 ml squared as your moment of inertia. This is the moment of inertia when you fix the axis of rotation to be at one end of the pen, and this is how we use parallel axis theorem. Okay, I hope this makes sense. Now let's get back to the beginning of this lecture. We were trying to find an analog of Newton's second law for angular motion. So far we have seen that A is the analog of alpha in angular motion, and for m, the analog in angular motion is the moment of inertia I. So what happens to summation of F equals ma, the linear version of Newton's second law, when we translate it over to rotational motion? Summation of something should be equal to replace mass with I, replace A with alpha, right? That makes sense. What is this something? This something is what we call tau. Tau, it's a Greek letter. This denotes torque. What is torque? Torque is the turning effect of a force that we apply in our everyday life every other minute or so. How? Torque is involved whenever we try to open a door, for instance. This torque depends on the size of the force, distance of the applied force from the axis of rotation, and the angle at which the force is applied. And using these things, we can write down a formula to calculate torques. Torque is equal to the magnitude of the force being applied to make something rotate or turn around a fixed axis, and r is the distance from the fixed axis of rotation to the point of application of the force, and theta is the angle that is formed between the force and the line that connects the axis to the point of application. And remember, theta should always be less than 90 degrees. Why? Let's think about it. Because this is a door in your room, and you usually open it by applying a force on the doorknob, right? And it opens around a hinge, which is the fixed axis. What happens if you come close to the hinge right here and apply a force instead of this force? Let's call this F2. Now you're not applying this force, you're just applying F2. What happens then? It becomes harder to open the door if you're applying a force very close to the hinge. If you apply the force directly at the hinge, you can't open it at all, no matter how hard you push. Another thing is, if you try to pull along the length of the door, that is, if you are applying a force that is in this parallel direction, let's call it F3, it is parallel to the fixed axis, nothing happens. There is no turning effect of the force. Let's get back to why these are the cases and why these are the dependence factors. The size of the force is pretty simple. The more force you apply, the higher the torque will be, right? That is pretty easy to understand. Now, the distance of the applied force from the axis of rotation. So if you try to open the door very close to the hinge by applying a force F2 very close to the hinge, it is very hard to open the door, right? So the farther away from the fixed axis you go and apply the force, the less force you have to apply to open the door, right? So that is how this is dependent on the distance of the applied force. So far we have learned that torque is directly proportional to the size of the force. The more force you apply, there is a chance of more torque, and also directly proportional to the distance away from the distance of application of the force away from the fixed axis of rotation. The farther you go away from the fixed axis of rotation, the less force you have to apply to cause the same amount of torque. Now it is also dependent on the angle at which the force is applied. If the angle at which the force is applied is 0, what is this angle? Let's look at. Angle is the angle between the force and the line connecting the axis to the force. The line connecting the axis to the force is this blue line right here, right? But if you're applying a force that is parallel to this line connecting the axis, what is the angle? Angle is 0. For 0, sine of 0 is 0, so you don't have any torque. If you apply a parallel force to your fixed axis, you don't have any torque because sine of that angle 0 is 0. What happens if you apply a force that is at a 90-degree angle to the line connecting the axis with that force? Say in this diagram, that should be in this direction, right? So that the angle formed with the R and the force, let's call this force F4. The angle formed is 90 degrees. If you apply a force that is perpendicular to the line connecting the point of rotation or the fixed axis R, then sine of 90 is equal to 1. That is the maximum value of sine theta. So that is the reason why you cannot have theta more than 90 degrees, because then you would have nonsensical repeating values, because sine always oscillates between -1 and +1. So sine of 90 degrees is 1, which is the maximum value, and the minimum value of torque is 0. Now you can say that, well, force was permitted to be negative because it was a vector. Now we have derived or connected Newton's second law to this Newton's second law for angular motion. Why cannot tau be negative? Well, tau is something called a pseudo vector. This is not a real vector in the complete sense of the word, because the direction of tau is not traditional vector like. For example, when we learned about usual vectors, we said direction was positive, negative, or at an angle to a certain axis. But tau and angular quantities in general, like alpha, omega, theta, their direction is with respect to the rotational motion. So we can say that the tau or torque or angular velocity, angular acceleration is at a clockwise direction, CW, or counterclockwise direction. So these are not vectors in the typical sense of the word, and so tau, the angle maximum you can use, is 90 degrees. All right, but it's not saying that tau cannot be negative. Tau cannot be negative by the choice of the angle. Tau can be negative with respect to the turning effect being clockwise or counterclockwise. Let me stop talking and examine an example. All right. So here we have a crane that picks up a heavy beam using this connecting cable, which exerts a tension to bring this crane up. Okay, so as we can see, the implied original position of the crane was lying horizontal on the ground, and the crane is picking it up by exerting a turning effect around this point O. All right, or exerting a torque around point O. It is 10 meters long, the heavy beam. The tension in the cable that is producing this torque is 2 times 10 to the 4 newtons. What is the torque exerted by the cable about point O? All right. So the first thing is, we used to draw force diagrams to work out problems using Newton's second law. We'll do the similar thing here, okay? But now let's call it a torque diagram. So we know that tension will always act along the length of wires or cables, so it will be always a pulling kind of force. So tension is directed like that. The tension in the cable is directed like so. Okay, that's the tension provided by the cable. The beam is, let's consider this to be the beam, okay, and this to be the point O, about which I am, or the tension is trying to exerting the tension is exerting a torque around O. Okay, the angle that is between the tension and this beam is 127 degrees. This is our fixed axis position, and we know that how do we define torque? Torque is defined as the magnitude of the force causing the torque times the distance from the fixed axis position to the force application point times the sine of the angle between the force and this R, right? The force application point and the line connecting the axis, fixed axis, to that force application. So what should that angle be? Should that be 127? No, we learned that theta is always between 0 and 90. So what is the angle then? Well, you can extend this cable, or actually not the cable, this beam, that would be the line joining the fixed axis to the force application point, and then the angle would be this thing, right? The angle between the force applied and the line joining the force application point to the fixed axis position. This angle is what? It is nothing but 180 minus 127, and this comes out to be 53 degrees. So this is what theta is in our formula. Okay, then what is the length of the beam? The length of the beam is given to us to be 10 meters. So it is also the distance from the force application point, because the force is applied at one end of this beam, to the fixed axis of rotation point, 10 meters. So now we have everything to work with. The torque produced by the tension force is equal to the size of the force, which is the tension, times the distance, which let's call this r, and the sine of the angle, sine of theta. Now let's plug in everything we know. But before we do that, we talked about tau being pseudo-vectors, and the direction of tau is relative to the rotational motion. It can be clockwise or counterclockwise, and with respect to counterclockwise or clockwise, we will assign tau a sign. Generally, we consider counterclockwise to be positive, but you can choose it oppositely. You can choose clockwise to be positive. Really doesn't matter. What kind of torque is tension producing here? Is it a counterclockwise or a clockwise torque? If you look at the fixed axis position, meaning the cable is actually causing a torque to rotate the beam like this around point O. So the rotation is going actually in this direction, meaning the torque produced by this cable and the tension is clockwise, meaning according to our convention, clockwise will be a negative torque. Now it is simply a matter of plugging in numbers. For T, plug in 2 times 10 to the power 4. For R, plug in 10. For theta, plug in 53. This gives me the torque exerted by the tension to be minus 1.6 times 10 to the 5 Newton meters. Now, Newton meters is the SI unit for torque, because torque is defined as force times distance. Distance is measured in units of length, meter. Force is measured in newtons. So SI unit for torque is Newton meters. I hope this whole discussion made some sense, and in the future lectures or future videos we will examine 1 or 2 more examples of torque.